My name is Jeff Cody. I'm a senior software engineer with Red Hat, working in QEMU, primarily in the block layer. And I am a sub-maintainer for block jobs and also some of the network drive image drivers for QEMU. So what I'm going to be talking about today relates specifically just to the block jobs. We're going to go over the status and some of the upcoming challenges. And also, at the end, we'll go over what the structure of a block job entails. So moving on to the status, before we get there, we'll go ahead and just define what a block job is, just make sure we're all on the same page as far as block jobs go. They are meant primarily to work with the management software layer like libvirt, but they can also be issued directly by a user. But the block jobs are defined as QMP commands as part of the Q API. And so all the block jobs are started by QMP or an HMP, in some cases, command. For instance, if we look at block commit, here's an example usage of block commit. That's the JSON that's sent over QMP doing block commit on the virtio 0 device. The point of the block jobs is to perform I/O tasks without having to pause to guest. So as we're doing the block jobs, we execute those in the coroutine, which is essentially a cooperative multitasking environment used inside QEMU. And this allows us to do our jobs asynchronously. So, and we can dial and adjust the speed threshold that job runs at to maximize guest performance or even the host requirements. And obviously, the whole point of the block jobs is to do I/O on the drive images. That might be modifying a drive image, might be reading from it, or creating new drive images, or shortening the whole drive image chain. So that's just kind of an overview of what block jobs are. We'll now look at what our current status is. I did the status from 2.2 since the last KVM forum. 2.2 came out shortly after that. It was a good starting point for the status. We have 4 block jobs currently in QEMU. We have backup, which, as the name implies, gives you a point-in-time backup to another image, either over a network or doesn't have to be over a network. And this is an area that's got a lot of work that's ongoing in QEMU now, and we'll get to that here in a little bit. We also have Blockstream. Blockstream is one of the older block jobs, and this is a way to move data around inside the chain. We can move data in the chain up into an overlay from a backing file. Then we have block commit, which is analogous to Blockstream, but in the opposite direction. We can move data from the overlay down into the backing file. Then we have block mirror as our last block job. And as it sounds like, we mirror drives write to a new destination, and we can mirror just new writes, or we can mirror all the data. And we'll also cover, in addition to those 4 block jobs and what is highlights what's gone on with those, we'll also cover some of the block job infrastructure changes and stuff to do in the future here. So if we start looking at backup, we have the block dev backup QMP command, which was added by FAM in around 2.3, I believe, is when the first official release where it'll be in. And the block dev backup command allows us to basically specify the the image we're going to be manipulating, not by having to specify it by the device string. Incremental sync mode was added. So this is a big one. It's a feature that's still ongoing. Added by John Snow. He gave a talk yesterday, a presentation on that. So a lot of information there. If you're interested in that, definitely check out his presentation. His slides are probably online somewhere now, and the presentation will be available sometime soon. There's also a QEMU wiki on the incremental sync mode and incremental backup. But in a nutshell, it allows, rather than have to do a full backup of everything in a drive image, it allows you to do what would be kind of a sane, rational way of doing backups, of doing a full backup and then doing incremental backups after that of just what's changed. And we also have some patches on the list. There's a Colo Sport, which is the coarse grain lock stepping. This is another area that had a presentation yesterday, and that, of course, will be online as well. But it's a way to provide high availability data replication. And these patches were submitted by Wen Kongyang, and there's also a wiki entry on this feature as well. So if we look at Blockstream, Blockstream didn't have quite as much things that made it in QEMU, but there's some stuff going on the list. But there were some minor bug fixes and cleanup in there, but mainly that was stuff that just happened to intersect into block job code, not necessarily intended specifically for Blockstream. But we do have, as far as patches on the list, we have some intermediate streaming support by Alberto Garcia. And he was here yesterday, but I think he had to head home today. But this patch series brings some feature parity to block streaming, similar to what was in place for block commit. Currently, when we are doing block streaming with what's in QEMU now, we can start from any given base image in the chain, but then everything between that and the active layer gets pushed up into the active layer. So in this case, we can take snap A, data in snap A, and data in snap B, and we can push that up into the active layer. But with Alberto's patches, it does what we can. Sorry, let me back up. We're able to then just move data from snap A, from one of the intermediate images, and move it to another intermediate image. So if we want to reduce the size of our chain, we don't have to collapse the whole chain all the way up to the active layer. We can just push data from one intermediate layer to another, and then drop that redundant image then. So those are patches on the list now, and I expect those will go in pretty early in the 2.5 cycle. Block commit. This one didn't have a whole lot of changes, mainly just some minor bug fixes and cleanup, and that's really about it. Block mirror has some more changes in there than definitely block commit did. Some of the stuff that made in the QEMU Git between 2.2 and now is a bitmap spoiling fix from Vladimir, and this fixed a bitmap issue when we added bitmap support for block mirror. And block mirror had its own bitmap, but it was using global bitmap manipulation functions for the entire block state, block driver state, which then would set or clear or reset dirty bitmaps that weren't intended to be cleared or reset. And FAM has patches for some bitmap scanning speedup that made it in for 2.4.0. And just recently, Kevin had a patch in for a coroutine reentry fix. This was a regression fix to prevent us from re-entering a coroutine when we did not expect to re-enter the coroutine, and only re-entering it when we actually intended to, or resuming it, I should say. And then also other minor bug fixes and cleanup occurred in block mirror. As far as block job infrastructure for what made it in, nested pause, which has nothing at all to do with nested vert, but it's patched by FAM for 2.4, and it allows us to pair up multiple block job pause and block job resume commands. So we have future challenges and some things that need to improve for 2.5. A couple of items on this list. One is op blockers, which stands for operational blockers. When we have block jobs, we have certain operations that we want to block and prevent from happening to keep the chain safe. We don't want to modify contents when it's not expecting to be modified, or when there's other operations or items in the chain that expect the contents to be a certain state, and then we modify that. We do have operational blockers in place that in the code that's been around for a while, but what we want to do is add some finer granularity to that, be able to run more block jobs in parallel, and also improve some of the locking safety that we currently have. And another area is a safer commit mode, and this really spun from a IRC conversation with Eric Blake. But the idea with the commit is inherently a risky operation, just due to the nature of how commit occurs. We have multiple images in a block device state chain, and we're taking data from the top or from somewhere in that chain, and we're pushing it down into backing files. The problem being is that each image in that chain is essentially a difference file from the image right before it. So when we push data down, images are no longer, so if we take data that's in active here that's different from what's in base, and we push it down, then snap A and snap B are most likely invalid because they're a difference off of something that is not expected. And this is expected behavior, however, for those two images become invalidated because they'll get dropped from the chain. The idea is you're doing this commit so that you can push all the data from here, here, and here down into the base, and then you drop snap A and you drop snap B from the chain. However, you might, for instance, have the block commit operation fail from, let's say, like a disk I/O error, or if you're doing over a network file system, you have a network error. And in that failed state, everything's okay when you're operating from the top of the chain, because everything down through here will be consistent as read through active, because only it, from its view, everything will be the same. However, it's possible that other tools may want to look directly at one of these other snapshots for some reason. Or it could be that outside of the QEMU process, there's another tool or piece of software that's looking at or relying on these two snapshots that QEMU has no way of knowing about. And this would typically be managed by the software management layer like libvirt. But of course, users can do things outside of any of our software, right, if they are determined enough. And so once this commit happens, these two are no longer valid. But what we can do to help mitigate that to a certain extent is we can try to be a little bit safer about how we do this by doing a hybrid stream and commit. Now, we don't want to stream everything in base up to snap A because that's slower and it's not necessary. What we want to do is we want to take just the sectors that are going to be changed from active going into base and stream those sectors up into snap A before we commit the sectors from active down into the base. And then once we commit those sectors from active down into the base, every image in this chain right here remains valid. They're all happy. as each one of these is a difference from the one previous, snap A sees those sectors inside of it, so it's not going to go and try to fetch those from base. Snap B, when it goes to read those sectors, will go down and look at snap A. Snap A will have them, and so we won't look at the modified sectors down in base. And of course, active, after this commit, we'll have these two images dropped and be looking straight at base. Or if that's not the case, it's still only looking at its own sectors. So everything remains valid except for some fringe cases, which QEMU has no way of preventing and would hopefully be prevented by the management software such as libvirt. And that would be if there was someone else had made outside of QEMU an overlay on base that's in parallel to the rest of this chain. Pushing data down here would invalidate that overlay, but we can't really do much about that. But we can help the kind of more standard normal use case be a little bit safer. There's also patches that are on the list that I don't have a slide up here for, but it's related to incremental backup. There's a whole area of that on transactional support and error handling that is most likely, I'm expecting to be available in 2.5. That's my assumption. So if we look at a structure of a block job, we have some key components of the block job. I'll try to speed it up here. We're running out of time. Block jobs are defined by a QMP command definition that's present in a JSON QAPI file, and also in the QMP commands.hx files. Between these two, this defines the auto-generated code that QEMU creates for marshaling of the data, and also where that points to the QMP handler functionality. Then you have your QMP command handler, which is in blockdev.c. This is the first piece of code that you actually write that handles the actual QMP command that comes from libvirt or whoever. And then you have the actual coroutine itself. For instance, blockstream.c is the streaming coroutine. And there are some rules you need to follow for the coroutine to make sure you play well. Since it is a cooperative multitasking, you don't want to hog the entire system or the entire QEMU thread there. And then you need to schedule your job completion and cleanup to run in the correct AIO context. So if we look at a sample block job, I wrote a block null block job driver for this presentation, and I've got some snippets of it on here and then a link to where you can see it on GitHub. But all it is, it's a simple block job that just goes through and reads all the sectors in the block device chain and just does nothing with it. The idea is to have a block job with all as much complexity stripped out as possible so that you can see where it goes. The code's available on Git here on my Git server, and also we'll have some snippets throughout here. But for the QMP command definition, this is what it looks like. So you have a block job type in the QAPI block core.json file. So we just added this null command right here for our new null job. And then we have our block null command definition in that same file. So those are, to implement a new block job, those are the only two items for this case that needed to be added in. Here's QMP Handler. I won't dwell on this screen that much because we're running short on time and it's a lot of code to just kind of stare out at the screen. But basically all it really does is it's going through this parsing argument from the QMP command. It's doing some validation, and then down here we actually initiate our coroutine right there. And the block job coroutine, I didn't put the function up here because it's rather long. It's not necessarily complex, but there's more code than would really fit on just one or two slides. But the idea is you have a coroutine loop, it's probably a while or a for loop or something like that. It needs to yield inside there using generally block job sleep. As I mentioned before, block jobs have a speed parameter that are passed to it. That's a maximum speed kind of for throttling. In the sleep time that you will yield inside of the block job will be calculated and derived from that throttle speed that's passed. And there's some functions that help you calculate that, so you can just pass that in. And of course, inside your coroutine, you're going to perform all the I/O you need to do, read or write, or even some chain manipulation. And you can see this is just a link for, if you're looking at the slides online, you can just click that and it'll show you the whole C file for the job null block job. So block jobs also have events. We have block job completed, block job canceled, block job error, and block job ready. These events are sent from QEMU over QMP, and management software like libvirt will parse these to determine what to do or to see events as they happen. They're pretty self-explanatory, except maybe the last one. Block job completed means the block job's been completed. Cancel means it's canceled. Error means there's an error. Block job ready is emitted for some block jobs where we may do some initial setup. There might be some operations that run before we kick off the entire block job. So QEMU will emit block job ready, and then the management software will come back with a command to initiate and complete the block job. Somewhat confusingly, the command is block job complete, which is easy to confuse with block job completed. But libvirt will send block job complete to initiate the completion of the block job. Mirror or active commit are a couple examples of ones that would use the block job ready and the block job complete kind of handshake there. So if we look at the block job control, there are some API functions defined to be sent over QMP to control block jobs. We can set the block job speed, set the maximum speed of the block job. We can cancel the block job. That will cause block job cancel to be emitted. We can pause the block job. We can resume it. And then the block job complete is the block job control command that I mentioned that you would send after receiving a block job ready if you were the management software or the human writing JSON to the QMP. So that's it. If you have any questions.
Maybe it was lame, but question is what space we will require in order to perform a block job commit. For example, if I have a base image of 1 terabyte and active image with 1 terabyte, which do not cover each other, how much space I will need to perform this job? 3 gigabytes or something around 2?
I'm not sure I caught all of the questions. So you're wondering if you have
I would like to truncate active delta in progress of block job commit to avoid disk space wastage.
Okay, so you have a block job that you're running, and you want to truncate that to make.
I would like to keep average space occupied by both images around 2 terabytes.
Okay.
I don't want to have 3 terabytes. It's a problem in real life.
Right, okay. So in that case, if you're trying to restrain the image size when you're doing the block commit, some of that's going to depend on the image file specification that the drive, whether it's QCal2 or a raw image file. But some of that calculation will have to be done by the management software on the amount of space that's free, because we don't have any way to when we're doing the block commit, we're going to commit all the clusters and sectors that need to be written down in there, and we're not going to stop the commit at some point, even if we're running out of room. Does that make sense?
Yes, we should truncate active image during the progress. For example, we are doing something like this in parallel server when we commit 128 megabytes of data. Get 128 megabytes, write them down, truncate. Get 128 megabytes, 128, sorry. Get 128 megabytes, write them down, truncate, and something like that.
So he wants to make it fast. Yes.
You want to make it fast progressively.
Yes.
Yeah.
It should be doable.
This is exactly what customers expect from merging.
Right. So essentially, what we want to do is in the active layer, when you're doing the commit down, we want to clear out unused sectors and zero those out inside the format. So yeah, that's something we need to do. Yeah.
Hi, you mentioned block stream for intermediate block streaming. You mentioned intermediate block streaming.
Yes.
Is there a specific use case for that, or is it to maintain symmetry between block stream and block commit? Because block commit allows you to commit into any of the intermediate images.
I don't know.
Yeah, Alberto, you said probably
Yeah,
he might have answered that, I guess.
Yeah,
Since the question
these
for
are
him.
these are patches. If I can find it, they're from Alberto. So I'm assuming that these are driven by some end use case, not just feature parity. But yeah, it would. I don't know the ultimate driving factor of it. Yeah. Right. Yeah. 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 All right. No, that's it. Thank you.